Welcome to GATE video session. The topic of maximum power transfer theorem. Today we are going to discuss about the maximum power transfer theorem basics and steps how to follow while solving the DC network. And third, we can solve few problems based on the maximum power transfer theorem. Fine. In the GATE syllabus for electrical engineering, under the electric circuit section, the maximum power transfer theorem will be asked in the network theorems. Fine. So what is mean maximum power transfer theorem? When a load resistance, resistive load being connected to DC network, receives maximum power when the load resistance RL is connected to Thevenin's equivalent resistance R Thevenin of the source network as viewed from its load terminals. Fine. That means, what is mean here? Thevenin's equivalent resistance mean the source circuit internal resistance which supplies the power to the load. Fine. So why we have to use maximum power transfer theorem? Finds the load resistance. In this network, actually, this is the sample network. In this network, this RL is the load and the remaining portion is called source internal network. Fine. So whenever this total resistance of Thevenin's resistance equal to the RL value, the maximum power transfer theorem will be proved. Fine. We can move on to the next slide. So the maximum power transfer theorem is basically applied for both an AC and DC network, but only the difference is when if you use the maximum power transfer theorem to the AC circuit, instead of resistance we have to substitute the value of impedance value. Only the difference is we have to substitute the value of, instead of resistance we have to substitute the impedance value. This is the difference between the AC network to the DC network to the AC network. Fine. So the maximum power transfer theorem and their applications majorly for, one is for communication system and second one for audio system. Where in the communication system, where we receive the low strengthened signal to maximize the signal, we can use this maximum power transfer theorem. And the second one, it is also used in the audio system where we want to amplify your amplifier to the speaker. So from these two places we can substitute. Fine. We have discussed the applications. The third application we have to think over whether this maximum power transfer theorem can apply it for our electrical power transmission system. So just think over. We can discuss the same point in this session. While completing this session, can we apply the maximum power transfer theorem to achieve the maximum power transfer in electrical power transmission system? Just think over. We can discuss this point at the end of this session. Great. So next we can move on to the steps for solving network using maximum power transfer theorem. So this is very important points we have to keep in our mind, because while solving the gate problems we have to follow these steps. Will be helpful for to achieve easily or to solve. We can get the value easily. Fine. The step one, first we have to remove the load resistance of the given circuit. First point, we have to remove the load resistance of the circuit. Step two, find the Thevenin's resistance of the source network, of the source network as viewed through open circuit load terminal, where the load resistance we are removed. From that point we have to calculate the Thevenin's resistance. So while calculating the Thevenin's resistance, as we know, we have to apply the Thevenin's rules. We know well. Fine. So step 3, As per the maximum power transfer theorem, R is load resistance of the network. Okay, or load resistance. So when the maximum power will be transferred, the condition should be RL equal to R Thevenin. In that condition, the maximum power can be transferred from source network to the load network. Fine. So how we can able to find? This is the equation to calculate the maximum power. P max equal to V Thevenin whole square divided by 4 divided by R Thevenin. Okay, fine. We can move on to the simple network. Okay, for explanation of a simple network. So here the aim of our maximum power transfer theorem is to determine the load resistance. Because why we are saying to determine the load resistance? See, the internal resistance of the circuit, the DC source network, is already fixed value. We cannot modify the value from this network. So only the point we can change the resistance of the load. Only the point we can change the resistance of the load. So that's why we are saying the load resistance. That's why we mentioned also here the RL is the variable resistance. Clear? So that we have mentioned this RL is the variable resistance. So in this resistance, if you change at a point when this RL is equal to R Thevenin, at that point the maximum power will be transferred from source to the load. This is the actual condition of the maximum power transfer theorem. Fine. So we will just solve and we will find the equation. What are the equation will helpful for to find the maximum power transfer theorem? First, in this network, first we have to apply a Ohm's law. So for the Ohm's law, we know that V equal to I into R. We know that V equal to I into R. So fine. So now this is called R Thevenin. This is the internal resistance, source internal resistance. Fine. So we have to apply, we have to find the current of the given network. Okay. So here the voltage, the Thevenin voltage is in series with the Thevenin resistance as well in series with the load resistance. So I equal to V Thevenin by R Thevenin plus RL. As for the Ohm's law, we know that well. Fine. So next, while calculating the power of the given network, we know that P equal to I square R. So here we are finding the load power. So we have to apply the PL I square RL. So we already known the value of current here. So we have to substitute here PL, that means value of current will be equal to V Thevenin by R Thevenin plus RL square into RL. Great. So this is the final equation to find the load power of the given DC network. Okay. So here, if you want to vary, if you are varying the R, so we have to P can be maximized by varying the R, and hence maximum power can be delivered when the differentiation of power by resistance equal to 0. This is the condition for deliver the maximum power of the given network. Correct? Fine. So next we can apply the differentiation formula for this to receive maximum power as per this condition for the given power source. Okay, for the given power. So here only the value, the variable value is RL. Okay, only the variable value is RL. So for dou P by dou L, differentiation of power, load power by differentiation of load resistance equal to, as per the formula given here, UV differentiation formula. Okay, we have to apply this UV differentiation formula for the given equation. For this, the equation we found for PL equal to V Thevenin by R Thevenin plus RL into RL. For this equation, we have to apply the UV differentiation formula. So if you apply, what we have the rules, UV rule, we have to follow the UV rule, dUV by dx. Dx means here is the RL equal to V. What is the V here? As for the V is here, R Thevenin plus RL is the V here, and for U is here is V Thevenin square into RL is our U. Correct? So here V into du by dx minus u into dv by dx. This, as for this formula, we have to substitute the power equation and to get to prove the maximum power can be transferred. So as for that, we are substituting. As we know that what is the V, we have to substitute the V square. So V square is the R Thevenin plus RL square whole square, okay, then into the R Thevenin plus RL square in the differentiation of d divided by dRL into V Thevenin squared into RL minus V Thevenin's RL into d by dRL into R Thevenin plus RL whole square. Okay, so we have to carefully solve this equation, then to get dou P L by dou RL is 0. Okay, so now you substitute this dou P into dou RL equal to 0. So what will happen? So now this portion will be get cancelled. Correct? This portion will be get cancelled. So if it's cancelled, we have to directly, we can substitute over here is 0. Okay, we can substitute over here 0. So now V Thevenin into R Thevenin minus RL divided by R Thevenin plus RL square is 0, which gives R Thevenin minus RL is 0, or we can say that R Thevenin is RL. So in this condition only, the maximum power can be transferred from source network to the load network. Okay, hence prove power from DC source network to a resistive load maximum when the resistance of the DC source network is to the load resistance. That is called R Thevenin equal to RL. Fine. Hope you are clear with this. Okay. So now this is a very important formula. While maybe if you are getting a gate question, this is an important formula. So P max equal to V Thevenin's whole square R Thevenin divided by R Thevenin plus R Thevenin. What happened here? We substituted over here. Instead of RL, here we proved that because R Thevenin and the RL are same, the values are same, so we are substituting this R load into R Thevenin. So it's that equal to V Thevenin's divided by 2, that means R Thevenin plus R Thevenin will be 2 R Thevenin, whole square will be 4 into R Thevenin. So after you substituting the values, you will get the final, the equation as V Thevenin square divided by 4 into R Thevenin. So this is the, you can just skip it. This is the equation number 3, is a very important equation to solve the gate problems. Okay, so equation 3 gives the, which is consumed by the load, the power transferred by the source will be also same as the power consumed by the load. Correct? So when we can able to achieve at the point of R Thevenin equal to RL. Right? Fine. So the total power supplied is given by the equation is P equal to 2 into V Thevenin by 4 R Thevenin. That means V Thevenin by 2 R Thevenin. Why? We have here V Thevenin by 4 R Thevenin, but here we have by 50%. Why? This is the point we asked the question at the starting of the session. Why can we use the maximum power transfer theorem into the power transmission network? Yes, we have to think over here. See, while we transferring the power from the source network to the load network, when the source resistance also the load resistance are equal, the total power will be consumed 50% from the source network and the remaining 50% will be consumed from the load network. So obviously we can able to achieve only the 50% of the source, that means source power to the load power. So that's why this we have to think over this point. So here this is the efficiency. From this efficiency you can easily understand rho equal to P max by P. So if you substitute that into 100, just if you cancel, you will get it only 50%. Okay, that means you can just substitute these two formulas. Okay, V Thevenin by 4 R Thevenin divided by V Thevenin by 2 R Thevenin over here. So we'll get it only 50%. Okay, so in this condition only the maximum power transfer theorem will satisfy in the network to transfer the maximum power to the load network. Okay, the concept of maximum power transfer theorem is that making the source resistance equal to the load resistance, then only to achieve maximum power transfer the source and the load resistance are matched, and with this efficiency become 50% with the flow of maximum power from the source to the load. Hope you are clear with that question. So in this question, you hopefully you can able to understand. So whether can be used? No, it's not efficient. If you are transferring only the 50% of the generated power to the load, is not possible. Why? The basically whatever the resistance we have, the load resistance being sufficiently greater value of the grid network. Okay, our grid network is sufficiently greater value. So that's why this condition may not be satisfied. That means our load will not be equal to the source network. So that's why because of the greater value, we cannot transfer the maximum power, and that's why this power also only the 50%. So the efficiency will not meet over to get here always for higher efficiency. So that's why what happened, the criterion of maximum power is very rarely used in the power system network. Hope you are clear with this. Okay, so next, using this formula, we can solve a simple network in the maximum power transfer theorem condition. So this is a simple network. Here you can see there are few internal resistance, also there is a load variable resistance and internal source. Fine. So first, the steps we have to keep in our mind. Just we can recollect the steps. The first step, we have to remove the load resistance. Okay, first step, we have to remove the load resistance from here. So then we have to find the R Thevenin value. Okay, we have to remove the load resistance and we have to find the load resistance. First, we have to remove the load resistance and we have to find the R Thevenin value as viewed from the removed load terminal point. Okay, so from here if you calculate the R Thevenin, so first these are the resistance are connected in series. Okay, it's called 3 and 1 and 1 will be the 5 ohms is connected in parallel with the 10 ohms. Okay, so 5 ohms and 10 plus 5 ohm are connected in parallel. Okay, great. So it's connected in parallel. So it will be, if you finally we can get it 8.33 ohm as a R Thevenin resistance of the given DC network. Okay. Second, we have to find the V Thevenin value. The second, we have to find the V Thevenin value. What is our V Thevenin value? How we can able to find? So from this load terminal, from the load remote terminal, okay, we have to calculate that. So V Thevenin plus 50 by 5. V Thevenin, okay, V Thevenin, we have to solve first this one. V Thevenin plus 50 by 5 plus V Thevenin by 10. Okay, V Thevenin by 10. Okay, then plus 0 because here there is no current flow. So that's why we cannot calculate this value. So after you solve this equation, we'll arrive this point, then we can find the V Thevenin value as 33.3 volt. Fine. So now we know the V Thevenin value and we know the R Thevenin value. What is our equation? Maximum power transfer theorem equation. PL equal to V Thevenin's whole square divided by 4 into R Thevenin. If you substitute these two values here, we can get as the maximum power will be transferred from the source network to the load will be the 3.28 watts. Okay, so hope you are clear with this session for the basics of maximum power transfer theorem and what are the steps how to follow while we solving the maximum power transfer theorem, and we have solved a simple problem. Hopefully you are very clear with these topics. Probably we can discuss further in the subsequent sessions. Thank you.